Hello, y'all. Darrell Berry Jr. here, back from some physics. And I'm in crunch time. I have an assignment due in the next hour. I'm going to go ahead and finish these problems with y'all's help. So go ahead and pop in. Let me know if you have any questions, comments. And let me actually change the scrolling text. So it'll be, what? Solving. And we'll do potential and mechanics. I'll go ahead and get started. I do have my foundational physics book up, even though we might not, probably won't end up using it. So I probably will switch to the single screen. Oh, interestingly enough, this book sits differently on the page. So what I'll do is switch to single screen with just my pad. And I have to remember that my battery is low. Maybe that can be a uh, motivation to try to finish before my battery punks out. We have this. When you all get in, remind me to scroll if I forget to scroll to show the higher part of my screen. All right. So I finished this first part. So now I need to show that the equilibrium position, uh, show that for small x, the potential takes the form of ux constant that. Let x be the displacement from equilibrium. So if I call, the idea is that I'm going to call equilibrium R naught. And my notes here, we have to take a Taylor expansion. I may do a video just on Taylor expansion sometime. Every time I have to do a Taylor expansion, I have to relook it up. Because I guess you do it consistently enough where you get familiar with it, but at the same time, at least for me, it's not enough to where I remember how to do it off the top of my head every time. So the first one is regular U naught, x minus, oh, hold up, r minus r naught to the 0th power and 0 factorial plus u r naught 1 r naught to the 1st power over 1 factorial plus u r naught to the 2nd power. So I guess maybe I should be doing hashes instead, because this is not the 1st power, but the 0th derivative, 1st derivative, 2nd derivative, r minus r naught squared over 2 factorial. And I didn't recognize this before, but when it says let x be the displacement from the equilibrium position, Professor had to point out that detail to me. R minus R naught is the displacement. So R minus R naught. So we're going to let that be x. So that means that I have UR equals, so the 0th power, anything to the 0th power is 1. So you have U x, or technically U R naught. That's not the displacement, that's just R naught. Plus, so I need to take the 1st derivative of U and then input R naught in it. And then it'll be x. And first factorial is 1. And then I have the d squared over dr squared of u r naught, and then x squared, and it should be a plus, and oh, the 2 factorial is going to be 2, so that's 1/2. So I have this. So this means I have u r naught plus. Now, earlier, I established that equilibrium is a critical point. And if you have an equilibrium, if you have a critical point, the first derivative, you set that equal to 0. So I solve for r at the first derivative. So r naught at the first derivative equals 0, according to what we did earlier. So this is 0 from earlier. And what I need to do now is take the second derivative of this thing. I'll go ahead and do that. So, and actually I already took the first derivative. So I believe this is the first derivative. Hope I didn't change much in it. So this is du over dr. So that means that, maybe I should simplify this a bit. Just check and make sure I didn't change anything too much. That, the inside. And that seems to be the first derivative. I don't think I made any adjustments to it, the next part already. So that means it's d, hold up, the dr is that. So d squared dr u equals d du. And I'm going to simplify this. So I'm going to have negative 2a over s times e try to do this all at one time. The negative 2a over s. I'm going to multiply this over here. Now I'm going to distribute that to both of these at the same time. So that's negative 2a over s e2 r minus r over s minus plus 2a over s e r minus r s. I believe that's correct. Oh, this is ugly. Just call this K now. So equals, so this equals u r naught plus, so the 1/2 is just going to be there. So 1/2 this x squared. So that means that a equals that. A equals this. That matches what they told us to get, and omega naught squared equals k over m. So omega naught equals square root of k over m. I think that is sufficient. Now the harder one is this one. So I have a cylinder. Let me actually just copy this image out. Cylinder, uniform density and mass with a frictionless axle along the symmetry. The axle is attached to a horizontal spring with a spring constant K equals 1.5 meters. Was released from rest at 15 centimeters from the equilibrium position. So A equals 15 centimeters. A is the amplitude. All right. So translational and rotational kinetic energies of the cylinder when it is passing through the equilibrium position. So what we consider is that this object has these two kinetic energies. So rotational has to do with the fact that it's spinning. It has a moment of inertia. So we would call 10 T rotational is going to be 1/2 we'll call it m v squared. V is the change in angle. If I call this angle phi, V is phi dot, and m is going to be the moment of inertia type uh, uh, mass. So let me look at my notes. Yeah. I need to add the I in addition to that. Have this where I is the moment of inertia of the rolling object, and P translational is 1/2 m v squared, or normal v squared, and I'll call this 1/2 m x dot squared, where the center of mass is moving along x. So we'll call this x. The center of mass is moving back and forth along this trajectory. Right. So basically the translational is the movement of the center of mass. The rotational is the movement of the actual rolling of the object. We have these two. And I think I'm good. Now, dealing with a spring, we have F equals negative AX. We know there's a force going on with this thing. And we know that force is the negative gradient of the potential. This means that force is the derivative of the potential. So that means that the potential is the integral of F with respect to x, which would be the integral of negative kx dx. So the potential, and it's the negative of that, drop my negative. So it's going to be kx2 1/2 plus v naught, and can uh, we call it define v such that v naught equals 0. So vx equals 1/2 kx squared. So being that we have these two, we can go ahead and utilize the Lagrangian, which is L equals T minus V. All you need is kinetic energy and potential energy to solve that. And I think everything. Yep. Seems like something is off with my um whatchamacallit. Take a look and see what I did the first time with the pen thing. It is MI. I don't know why I dropped off my M on that point. I just have I. I need to look this up. I'll look up rotational kinetic energy. Yeah, it is just I omega squared. I don't know why I have an M there. So, what is this thing again? A cylinder. So let me look up the moment of inertia for a cylinder. Let me actually before I do that, Let me show cylinder. At a moment of inertia for a cylinder, a solid cylinder, which it seems to be solid because there's a, brace catching the center. Uh, I equals 1/2 m squared. Oh, the moment of inertia has the m, so we have the full kinetic energy equals Tr plus Tt equals 1/2 I dot squared plus 1 m x dot and V equals 1/2 k x squared. And a constraint that we could apply to this situation, since we're using the Lagrangian, is that as this thing rolls, it will equal x. So in other words, the distance here that it rolled along the ground, for instance, will be related to the distance here. So we can say that x equals, I don't think they gave us a radius. Did they give us a radius? Mm, so, okay. So I'll just call this r. So x equals phi r, for its arc length. So x dot equals phi dot r. I can put this all in the same, in other words, I can use this constraint to eliminate one of my variables. I could either eliminate x or I can eliminate phi. My professor chose to eliminate x. So then I'll have um, x dot here, x here, and I could just have x there. So that'll simplify my Lagrangian. I don't have to do a Lagrangian with two variables. So that makes sense. So I can say that phi dot equals x dot over r. So this will equal 1/2 I x dot over r squared plus uh 1/2 m dot squared for the center of mass. So that seems good. Let me check my notes from my professor. Think that is okay. So you can simplify this one more actually and say it equals x dot squared over 2 I over r squared plus m. So that looks okay. And this equals t. Now I can do my Lagrangian. L equals t minus v equals x dot 2 I over r squared plus m minus 1/2 k x squared. So to use my Lagrangian, I'll just have one in x since I eliminated one of the variables with the constraint. We have d d uh, t, because that's the independent variable. They're varying according to time. d dt partial L over partial x dot minus partial L over partial x plus partial F over partial x lambda equals 0. I'm going to go ahead and use the constraint. And then once someone is passing through the equilibrium, I need to solve the Lagrangian. Not sure I do. No K, I do know K. Okay, passing through equilibrium. And actually, I might be able to pass up on this. So passing through equilibrium, KE equals max and PE equals 0. But E max equals PE max. PE max equals 1/2 k x squared. X is max. Starting to remember something my professor was saying about how the friction is going to lessen the kinetic. No, hold on. The maximum is going to not quite be the same because the uh, kinetic and the friction is going to lessen things. I do have to go to the Lagrangian. I'm just not sure how the Lagrangian will help me when I get there, but we'll see. I'll try it out. So this gives me force of constraint. Right? So we'll do 1, 2, 3. So 1 d dt of partial L partial x dot equals d dt of x dot I over r squared plus m equals x dot dot I over r squared plus m, and all the other terms are constants. So then we have partial L over partial x, which is going to be negative kx, and partial f over partial x equals so f equals, which one am I going to make 0? X dot minus 5 dot r equals 0. This which one am I going to make negative? Okay. I use this one. Uh, so be my constraint without the derivative. So partial f partial x equals 1. Right, so we're okay. So partial f over partial x lambda equals lambda. So that means that we have x dot dot I over r squared plus m plus x plus lambda equals 0. And to 0. No, can solve for lambda. So lambda equals x. I'll just copy it. So that's the force of constraint. That's the friction force. Well, I mean, since the units are right, kx equals newtons over meters. Meters equals newtons. And this is meters per second squared. The moment of inertia is going to be kilograms Meter squared, meters. Oh, divided by r squared. I mean, times mass, that's mass, but meters. Kilograms, if it's over meters squared. So this cancels, this cancels. So you have kilograms, meters per second squared plus kilograms, meters per second squared plus newtons equals newtons, because newtons is kilograms meters per second squared. So this, I mean, this is a force equation. So the force of friction should be this. The plug that in. That just means I have double thing. Well, should I did when I part it over. I need to put a negative there. Yeah, because the force is moving in the opposite direction from the movement. The only thing I'm stuck on, oh, you know what it is? If I'm going to use the Lagrangian, I can't eliminate some of the variables. I eliminated one of the variables, so I can't do that. That's what's getting me stuck. So I do have the force equation if I did not eliminate one of the variables. Delete this. So then I have everything is the same except this. This. Right. So now we can actually solve. So we have x dot dot equals negative ax divided by I over r squared plus m equals negative alpha x. Just say alpha equals k over and cylinder equals 1/2 m r squared alpha equals k over 2 plus m. So that equals 3m over 2. 3m over 2. So 2/3 k over m, if I did the algebra right. So x dot dot equals negative 2/3 k over m. X. I did this right. And I believe I looked up the proper value for the ordinance of the cylinder, 1/2 mr squared. So the 1/2 stays there, stays there, r squared disappears, 1/2 m over 2, m over 2. I think that is right. Oh, you know what I can do? I can actually integrate this thing. So now I have x dot equals negative the 1/3 k over m x squared, and integrate it again to get x. I think that's sufficient. So we can say that at 15 centimeters, which equals it's really 0.15 meters. Isn't that going to lessen the that's odd. So I put in 15 meters, it gets bigger. But if I put in 15 centimeters, the fraction seems to make it smaller. I'll just pop it in. So x dot equals negative 1/3 k over m 0.15 squared, which equals negative 1/3. K is 1.5 over kilograms times 0.15 squared. So that equals, see here, T. So kilograms meters per second squared. Kilograms over second squared. 1/2 squared. That's meters squared over second squared. I made some mistake somewhere. I'm not sure where. I forgot to square something. Seem to have the, what's gonna call them, right? X dot squared over 2 over R squared plus M minus 1/2 KX squared. Seeing if I missed something. That square for a cylinder. Why aren't the units working? Oh, I'm gonna units are not working. All right, I have to look at this problem again and see what I'm missing on the units here. Look one more time, see if there's something I can catch right now. All right, so I'm not sure what that is. But I'll look over it. I'll see if I can figure it out. I may come back tomorrow and I'll do a follow-up. But I'll look at this again and try to see what's going on. Uh, Omega equals K over M, but kilograms. So that equals divided by 0.5 kilograms. 3 uh, so kilograms per 3. All right, so at least we got that part. So I'll see you all tomorrow, I'm sure. I'll see if I can get more details on that problem. Have a good one.